Imagine using a cutting-edge AI to write your code base, only to have it spit out this incredibly dense, point-free alphabet soup of Haskell.
Right, which is mathematically flawless to the machine,
But completely unreadable to you as a developer. Yeah, exactly. You just sit there staring at this wall of composition operators, and you realize that while the compiler might love it, your human brain just, well, it can't actually parse the data flow.
it's just a wall of punctuation at that point.
It really is. So, welcome to today's deep dive. We are unpacking a highly specific and honestly fascinating blog post by a developer named Ang. It's titled Notes on Haskell Programming, Part 136.
And, I mean, that title alone, Part 136, that really signals we are jumping into the deep end of an ongoing architectural journey here.
Oh, for sure.
Ang is dealing with this massive friction between how machines optimize execution and how we, humans actually model domain problems.
Yeah.
We're looking at this classic tension in functional programming.
Right, that disconnect between algorithmic purity and maintainable, readable architecture. And the mission for our deep dive today isn't just to review Haskell syntax, We are tracing the evolution of a single problem, which is optimizing document generation using Pandoc's abstract syntax tree, or AST.
Which is a great use case.
Yeah, and we're going to look at how Ang starts with that unreadable AI-generated code, steps back to a really messy, naive human implementation, and then eventually arrives at an elegant solution that perfectly leverages the mechanics of modern compilers.
And that contrast is just striking because point-free style, where you write functions without explicitly defining the arguments they operate on, it's actually really idiomatic for seasoned Haskell developers.
Right, because it reduces visual noise.
Exactly. But when you are learning an API like Pandoc and you're trying to understand the concrete structural transformations of your data, point-free style just obscures the very architecture you're trying to learn.
Like we said, alphabet soup.
Right. It just looks like random punctuation.
Okay, let's unpack this. Because Ang actually abandons the AI's alphabet soup to examine their own original naive implementation. This was the code they wrote while still getting familiar with the Pandoc API.
Yeah, you have to tear down the flawed approach first.
Exactly. To appreciate the final architectural pivot, we need to understand the mess. So Ang was trying to take a flat list of parsed text tokens, so things like a header token followed by a paragraph token, and convert them into a fully formed Pandoc document.
And the initial logic followed a very object-oriented instinct, which honestly is a really common trap when moving to functional paradigms.
Oh, totally.
Ang's code looped through the token list, took a single token, and immediately applied the doc function to it. So this spun up an entirely independent, fully structured Pandoc document to hold that single piece of content.
Right.
Then the code used mempty as the monoid identity to just smash all these separate fully formed documents together.
And let's look at the mechanics of that, because Haskell applies functions inside out or right to left when you're using the composition operator.
Yes.
So the code starts with a blank Pandoc document wrapper, the mempty. It applies the author metadata, appends the title, and then for every single token, it generates that standalone document wrapper just to merge it into the main one.
Yep.
Wait, so generating a full document structure for just one paragraph, it's like building an entire fully furnished house just to store a single chair.
That is a great way to put it.
And then because you have 50 chairs, you build 50 separate houses, and you try to smash all 50 houses together to make one living room. I mean, why would the system even allow you to do something so wildly wasteful?
Well, what's fascinating here is that the system allows it because it works functionally.
Really?
Yeah, but the memory allocation overhead for that is staggering.
Yeah.
You were forcing the runtime to instantiate the top-level AST node, the metadata field, all the structural wrappers over and over.
To throw them away.
Exactly, only to immediately throw those wrappers away during the merge operation. You were just churning through the garbage collector for absolutely no structural benefit.
But wait, if we are dealing with GHC, the Glasgow Haskell compiler, which we know has incredibly aggressive optimization passes, why doesn't the compiler flag this?
Because GHC optimizes operational execution, not domain logic.
Oh, I see. Shouldn't it see that we are allocating and destroying massive AST nodes redundantly, though? Like, just optimize those wrappers away?
No, because the compiler doesn't know what a document conceptually means compared to, say, a simple text string. As far as the type system is concerned, merging two documents is a perfectly valid monoidal operation.
So it just assumes you know what you're doing.
Right. The compiler assumes you built those 50 houses because your specific domain required 50 houses. It dutifully executes your incredibly inefficient architecture at blistering speed, but it cannot fix a fundamentally flawed mental model of the data structure.
Wow. Okay, so that forces Aang to dig into the actual Pandoc documentation to understand the AST they are manipulating. And that leads to a critical realization about the data model.
The architecture shift.
Exactly. The Pandoc AST actually strictly separates its structure. So at the top level, you have a single metadata block. That's the title, the author, the date.
Right.
And completely distinct from that is the content list, which contains the block elements, the fundamental types for headers, paragraphs, and lists.
And recognizing that separation is where the architecture finally shifts from naive to idiomatic. By understanding that metadata and blocks are distinct, Aang refactors the code to use the block element itself as the monoid, rather than the top-level document.
Here's where it gets really interesting, because this completely changes the mathematical context of the program. In the original code, mempty represented an empty, fully formed Pandoc document, right?
Correct.
But in the refactored code, mempty acts as the identity for a list of blocks. We are no longer calculating document plus document.
Right, you're mapping over the tokens.
Exactly, turning them into blocks and combining them. So it's mempty block plus header block plus paragraph block.
And if we connect this to the bigger picture, we are deferring the heavy allocation. The refactored code merges the lightweight content blocks first, generating the entire body of the text in memory.
Oh, that makes so much sense.
Yeah, only after the entire list of blocks is resolved does it apply the heavy document wrapper and attach the metadata. So returning to your analogy, you build all the chairs and tables first, group them together, and then build one single house to contain them.
So much more efficient. It aligns the code execution with the actual reality of the data structure.
Exactly.
But looking at the source, the refactor introduces what looks like a massive new bottleneck.
Right, the apply meta function.
Yeah. When we examine the new apply meta function, which is the part responsible for attaching the author and title at the end, it uses a list comprehension to scan the token list, specifically looking for those metadata tags.
And on the surface, the time complexity there looks terrible.
That was exactly my thought when I read it. Like, hold on, doesn't this mean we are making 2 full passes over the token list? One pass to build the blocks and one to find the metadata.
It looks like we traded a garbage collection nightmare for a CPU bottleneck.
Right. We shifted from an ON memory problem to an O2N processing problem. So what does this all mean? Did we actually make it worse?
Well, it looks like a double pass if you analyze it through the lens of a strict, eagerly evaluated language. But in Haskell, that inefficiency is entirely an illusion, thanks to lazy evaluation.
Oh, right. Aang uses a really great analogy for this in the post, contrasting strict, eager evaluation with lazy evaluation.
The food analogy.
Yeah, eager evaluation is like an economy rice stall or like a buffet. The kitchen cooks every single dish in advance. The processing happens proactively, pushing all the data into memory arrays, regardless of whether the downstream functions actually consume it.
Exactly. Whereas Haskell operates more like a chef in a high-end restaurant who absolutely refuses to turn on the stove until a specific order is placed.
I love that.
So when Haskell encounters that list comprehension in apply meta, it doesn't actually iterate through the array right then. It creates a thunk.
A thunk.
Yeah, a thunk is a lightweight, unevaluated promise to compute the list later, but only if another function explicitly demands it.
Okay, but the apply meta function does demand it, right? I mean, it needs the title and the author to finish the document structure. This raises an important question. How does the compiler know when to stop evaluating the thunk?
Right.
Like, what prevents it from scanning all 10,000 tokens just in case there's a second author tag hiding at the bottom of the file?
That is where the pattern matching in the function dictates the strictness. In standard document parsing, metadata tokens almost universally sit at the very top of the file.
Oh, true.
The apply meta function is essentially asking the runtime for the very first instance of a title and an author. As Haskell begins forcing the thunk, evaluating the tokens one by one, it finds the title. Then it finds the author. And at that exact moment, the conditions of the pattern match are satisfied.
So the order is fulfilled, and the chef just turns off the stove.
Precisely. The function returns the requested values, and the thunk for the remaining, say, 9,998 tokens is simply discarded.
Wow.
It is never forced. There was no second pass over the bulk of the document. The runtime only did exactly enough work to satisfy the immediate data dependency.
That completely flips the script on how you'd normally analyze performance bottlenecks. Because the code on the screen looks like a redundant loop, but the runtime behavior is inherently short-circuiting it.
Right, it's an illusion.
But Ang notes that lazy evaluation is actually only half of the story here. The GHC compiler has another even deeper optimization happening at compile time to handle the list processing, right? Stream fusion.
Yes, so lazy evaluation handles when the data is processed at runtime, but stream fusion dictates how the memory is managed during that processing.
Okay, break that down for me.
Sure, stream fusion is a compile time optimization where GHC uses rewrite rules to eliminate intermediate data structures entirely when chaining operations on a list.
And Ang actually visualizes this by having the AI draft the logic in C, which is brilliant because it exposes the manual memory management that Haskell usually just hides from us.
Exactly. If you are working without fusion, so in an eager paradigm like C, you have to allocate temporary arrays for every single step of a pipeline.
Right.
If you map over a list and then filter it, you use malloc to carve out memory for the mapped list, read that into the CPU, run the filter, malloc a new array for the filtered results, and then free the old memory.
Which means the CPU is spending more cycles managing the memory bounds and shuffling pointers than it is actually computing your domain logic.
It's terribly inefficient. Every intermediate step generates a tangible data structure that must be written to RAM and read back out.
To translate that eager approach to a physical process for your listening, it's like an inefficient car factory.
Yeah, the car factory analogy.
Yeah, so imagine you bolt the doors onto the frame, right? Then you drive the unfinished car out to a holding lot, park it, realize you need to paint the doors, drive the car back inside, paint it, and drive it back out to the lot again. You are constantly stopping the workflow to store the intermediate product.
And the I/O overhead of parking the car just destroys your throughput.
Exactly. But the fused approach, which is what GHC does behind the scenes, is a modern assembly line. The car never stops moving. It rolls down the line, a robotic arm attaches the door, and 3 feet later, while the chassis is still in continuous motion, the next arm paints it.
Right.
The operations are fused into one continuous loop without ever utilizing a holding line.
And to translate that assembly line back into compiler mechanics, GHC basically looks at your chain functions, say a map followed by a filter, and it checks its internal registry of rewrite rules. It recognizes that mapping and filtering can be mathematically combined into a single recursive loop. So at compile time, it rewrites your high-level human-readable pipeline into a single, tightly optimized machine loop. It entirely eliminates the intermediate list allocations.
So as a developer, you get to write modular, composable functions that look like distinct, separate passes over the data.
Because it makes logical sense to your brain.
Right, it's readable. But the compiler secretly translates it into a single, continuous, fused traversal that is just incredibly light on the garbage collector.
It is really the ultimate synthesis of human intention and machine efficiency. You aren't forced to write unreadable manual loops just to save memory.
You just lean on the compiler.
Exactly. You lean on the compiler's rewrite rules to bridge the gap between your declarative architecture and the hardware's execution constraints.
Okay, let's pull all these threads together. We started with Ang staring down dense, mathematically pure AI code that offered zero insight into the actual data model.
Alphabet soup.
Total alphabet soup. And we broke down the naive human approach, exposing the massive memory overhead of building full AST wrappers for single tokens.
Which forced the realization that we needed to align our code with the actual architecture of the Pandoc AST, separating the metadata blocks from the content blocks, and shifting our monoid operations to the block level.
Yes. And from there, we peeled back the layers of the Haskell runtime. We saw how lazy evaluation turned a perceived O2N double pass into a super efficient short circuit.
The chef turning off the stove.
Exactly. And how stream fusion allowed GHC to optimize sequential list operations into a single intermediate free loop at compile time, like the assembly line.
And the overarching lesson here is that performance optimization isn't just about tweaking syntax or, playing code golf.
Right.
It requires a profound understanding of two things: the strict structural shape of your data and the evaluation model of your tooling. When you align your domain logic with those two pillars, the performance almost takes care of itself.
It really does. But, the journey doesn't end there, which is perhaps the best part of Ang's post. Because after achieving this highly optimized, deeply understood architecture, Ang finishes drafting the blog post and has this unexpected epiphany.
Ah, the classic developer's curse.
Right. The moment you push to production, you instantly see the flaw in your premise.
No, always.
Ang realizes there is an entirely different even more efficient approach for mapping the parser tokens directly to Pandoc's AST without relying on the token list reduction at all.
It's a complete paradigm shift.
Yeah, and it will be the focus of their next post.
Which really just highlights that optimization is rarely a destination. It is an iterative process of uncovering deeper and deeper abstractions.
Which leaves us with a really compelling final thought for today. We spend so much of our careers working tirelessly to optimize our systems, refactoring code, streamlining workflows, eliminating inefficiencies. But how often is our perfect optimized solution actually just a necessary temporary stepping stone? How often does reaching what we think is the finish line merely shift our perspective just enough so we can finally see an entirely different paradigm that we were completely blind to before?
I mean, the architecture is never really finished, right? It just waits for the next abstraction.
It really is a constant evolution.
That's
Well, thanks for joining us on this deep dive, everyone. We will catch you on the next one.